I think that some people will come. Okay, hello everyone. So thank you first of all, Nguyen, to organize this exciting seminar for young
Hello.
I think that there's some problem. No? Everyone hear me?
Yes. I lost the connection, it seems.
All right, so it seems that there's some problem, but so Hai-Sơn is okay? Yeah, the moment Nguyen see record the video, I think that the Zoom they ask you to accept or not, or you can quit.
I did accept, but then there is I lost the connection. Yes, now it seems okay.
Okay, so first of all, thank you, Nguyen, to organize on this exciting seminar. And today we are very happy to have Professor Hai-Sơn from Lyon with us. And I think according to our discussion, Hai-Sơn will present first about his let's say his CV. So I don't know if I really need to introduce in detail of what Hai-Sơn did in France and what he's doing now, but maybe few words about him. And then I think in the second part, Hai-Sơn will give us a very excellent talk about one of the topic he is doing now in his lab. So I know Hai-Sơn since long time. Hai-Sơn, right, is I think it's almost at the end of Hai-Sơn PhD at ENS Paris.
Yeah. Yes.
And then Hai-Sơn, so Hai-Sơn first come to France and study in one very famous university in France. We call Ecole Supérieure. So we have 4 Ecole Supérieure in France, and this is the famous one in Paris Center. So Hai-Sơn got a bachelor and master degree in that university, and then he continued PhD in the one famous laboratory of the same university, and he got PhD diploma in 2011. And then starting from that moment, I know Hai-Sơn because he come to my lab from time to time because he his first postdoc in one joint project between one CLS laboratory and my laboratory at that moment. And then after 3 or 4 years, Hai-Sơn, right, Professor Hai-Sơn got associate professor position in Lyon. We call Ecole Centrale de Lyon, so Central University of Lyon, also one of famous university in France. And then, of course, from time to time, I meet Hai-Sơn in France or in the conference in Vietnam. And we also meet each other via the website because Hai-Sơn, what Hai-Sơn did and what I do is quite close. And I hope that after this meeting, we can have some kind of collaboration. Thanks to his excellent research and also teaching, Hai-Sơn got a very beautiful position at what we call Institut Universitaire de France, EUF, for 5 years. For the first time 5 years, but he can ask for the second term. And with that, he can have some financial support for his research and teaching. And in particular, he can have more time for research and very limited teaching service, right, Hai-Sơn? Yes. So he can travel everywhere. He can travel everywhere. So if you have a chance to invite him to spend some time in your lab, you can invite him. He have more time now. So Hai-Sơn do a lot of interesting things related to optic light matter interaction. And today he will show us that one of the topic what he is doing, but he do a lot of things related to optical lattice matter metasurface. In particular, what he showed us today concerning photonic crystal and some interesting properties of photonic crystal. but in the past and also now he is doing something related to perovskite, in particular perovskite for light-emitting diode, laser system, and so on. But he also continue what he did in PhD related to single photon source, coupling with photonic structure and so on. So that is what I and Hyson and some other colleagues is discussing to work together for next few years. So I think that I don't need to say more because Hyson will introduce himself a lot of key point for. So I now let's Hyson to start and share with us his expertise.
Yes. So thank you, India, for a very nice and also detailed introduction. So actually, I did prepare some slides for my scientific careers and so on, but unfortunately, I forgot to save it, and there was some problem with PowerPoint. So this part of the CV now is not anymore in the presentation, but Professor Diep has a very nice introduction, and so this, since I don't have the slides anymore, just to show you that every information relating to my short CV and also publication can be found on my personal website that I show you here. But Professor Diep already did the perfect introduction. So I spent the whole university studying and also research career in France. So I left Vietnam after high school and went to France in 2003. And since then, I stay in France for studying physics, now teaching physics and researching physics. And even in Vietnam, when I was a high school student, I already loved physics a lot, and in the specialized school in physics. So also, as Professor Diep already mentioned, I spent also the first part of my studying and also research in the Parisian region. So until 2014, when I got the associate professor position at Lyon, the Lyon Institute of Nanotechnology. So this our institute is a very big laboratory. We have like almost 200 people, and even my research group called ILUN, like engineering light properties, is already have 50 people with 25 permanent researcher and teachers. So we are a very big group, and in the group we have different activities, but most of the activities are related to how to make photonic device, how to play with light, and how to make things more interesting by changing how light and matter interact with each other. And also, of course, developing applications from laser, diodes, solar cells, sensoring, working both in the linear regime, nonlinear regime with different wavelengths, starting from the UV, visible, infrared, up to mid-infrared. So for my research, as shown here in my website, I work in three main topics, but both related to how to engineer light matter interaction in nanostructure. So my three main topics is first, I develop a lot of theoretical concepts. So as I forgot to mention that I start my PhD as an experimentalist, but now I do more and more like theoreticians, but still doing a lot of experiment. So I can discuss with both experimental and theoretical physics. And I like it a lot, because when I was an experimentalist, sometimes it's very difficult to discuss with theoreticians. And I see also that the theoreticians, sometimes they don't know how to use a good language, how to experimental work. So sometimes we are talking about the same thing or trying to explain to each other the same thing, but we cannot make the connection. So now since I doing both, I feel very fulfilled, because now I can discuss with both of them. Okay, so a lot of my theoretician works is try to develop new concepts of photonics resonance in periodic lattices that we call metasurface. So how we can control light confinement, how we can engineer new properties, like we call now topological properties. But then I also do using this concept to make applications. So most of my applications works based on perovskite material, which is emerging materials that people first know for solar cells applications. But nowadays, and also in my research, I mostly focus on the light emitting properties of this material. So to make perovskite LED, perovskite lasers, I will show you some results today on the perovskite lasing, and also figure out how to put this perovskite material and light in the so-called strong coupling regime. That I don't have time to mention today, this strong coupling regime. And the third part of my research is something that I start already during my PhD, is not working on the strong emission light like lasing, but in the other extremities, how photons are emitted one by one. We call the single photon source. They are flying qubits for quantum information. And during my PhD, I worked more on like some kind of 3-5 quantum dot emitting in the near infrared. But now I shift into more like telecom wavelength single photon source, and which can be implemented into CMOS platform, which are the one of the microelectronics industry. So this that's all. So I think now you know a little bit my research CV, and now we can go directly to the presentation. Let's go to the full screen. Yes. And I have some problem. It's not going to the full screen. Okay. Do you see it?
Yes.
Okay. So today I try to convince you that we can teach light appearance new tricks in the sub-wavelength scale, and more precisely is how to shape photonic band on demand and taming losses at will. So I will start with something that most of us already know, and is the color of blue butterfly. Actually, this is a picture of the Morphos cypris, the Latin name, native butterfly living in Colombia. So this butterfly is very famous because actually the wings show a very vibrant blue. So it's this famous blue butterfly. You can find a lot of pictures of it. It's very nice. But then if you look closely to this color that people don't mention a lot, but actually this color depends strongly on viewing angle. So if you look at like normal like light emitting directly at zero emission angle or close to zero, you have this nice blue color. But if you tilt the angle up to like 50 or 60 degrees, then the color changes and it's not a blue anymore. It's some kind of fat color. And what is the origin of this butterfly effect? This actually will be the motivation of my talk today, because when you look closely to the wings, you can take this is the microscopic picture. You see that there are some kind of small feature, okay, and this one feature gives us the color. For example, here is the zero angle. This is 60 degrees, so you can see that the color changes. The question is this color is coming from this feature? So now in order to make a better zoom, people use scanning electronic microscopy. So you see that, okay, you have this rectangular shape about 100 micrometer scale. So it's already very small, but it's still very big with respect to the light wavelength. You see the light wavelength, the visible wavelength is something between 400 nanometer to 700 nanometer. So this 100 micrometer scale is much bigger than the wavelength. So with light wave, go to this kind of this structure, is consider that is something flat. The light is very small because the wavelength of light is very small, cannot recognize this kind of a pattern. But then if you look closer and closer again, each of these rectangular pattern actually is formed by a lot of parallel stripe. Okay, and now the pitch or the period or the distance between two parallel stripe is in the visible wavelength scale. You see that it's smaller than 1 micrometer. So light, when going to this kind of things, can say, okay, I see this fluctuation, this variation, and I react to this. You can see this like a wave propagate, C wave propagate and meeting some kind of rocks, and then so this will scatter. But now we don't have rocks, we have something periodic. A lot of rocks putting one close to the other one, and then light wave try to scatter this periodic feature, making interference and diffraction pattern. So this is the origin of the blue color. So indeed, actually, these periodic features that we call photonic crystal. So the crystal, because it's a periodic, and photonic because the refractive index change periodically with the period in the range of smaller than the wavelength scale. We call sub-wavelength scale. And then the blue color is obtained from the blue resonance in the reflectivity spectrum. So you shine light on the photonic crystal. Light here is some light, contains every color, every wavelength, and then you measure the reflectivity. We'll have blue resonances, and these blue resonances give you the blue color. Okay. So far so good. But then you remember that the color change with angle. So actually, the resonance wavelength depend on the angle. You have the normal incidences can be the blue resonances, but then if you change the angle, or how you look at these butterfly wings, and the resonance wavelength can change. So, and it depends on angle. So it's something very nice, and when you can merge it actually. But how we can relate it? This wavelength depends on angle, on some other physical quantities that people use in most of the case for different kind of system. So we talk about energy. So energy is related to wavelength by the very simple equation here. So E is equal to hc divided by lambda. H is a Planck constant, and c is the speed of light. So you can convert the wavelength into the photon energy. And then the angle, n, also the wavelength, can be converted into the in-plane wave vector of light. So you have like k in plane is equal to pi divided by lambda times sinus theta. So theta and lambda is related to E and K. So that means we can change the relationship between the wavelength depend on angle into energy depend on the momentum. And the energy depend on momentum is something we learn a lot in physics. We call dispersion of photonic resonances. So the energy depend on the momentum. When the dependence is not trivial, you have a non-trivial dispersion. And you have different resonances. You have non-ensemble resonances. Each resonances can exhibit a different dispersion, and together they form the so-called photonic band structure. So the notion of band structure is something we learn, not for light, not for photons. We learn in our semiconductor or solid state lectures. It's another kind of crystals, but it's still a crystal. So you remember when we in our solid state courses, we have like solid crystal. The period is very small. It's like angstrom, but then it's comparable to the wavelength of electrons. And instead of solving the electronics as a photonics system, in what we learn in our solid state lecture is okay. We can solve the equation for how electrons propagate in a solid crystal, and to obtain the band structure. So remember this kind of band structure, the y-axis is energy and the x-axis is momentum. Okay, so different big capital letter here correspond to different high symmetry points in the crystal, in the mirroring zones of the crystals. And then we measure the dispersion along different momentum direction. And again, you can have something very complicated that sometimes we call this as like spaghetti diagrams. And these kind of spaghetti diagrams for electrons you can find again for photons in photonic crystals. So here is an example of the photonic crystal band structure. We also have the frequency or energy versus momentum in different orientation or direction. And like semiconductor, you have the band gap for electrons. For photons, you have also photonic band gap. The photonic band gap is the energy interval that photonic modes cannot exist. It's forbidden. The main difference between these two is that the electronic wave function are scalar, and the photonic wave function, which is a light field, is vectorial. You have electric field and magnetic field. So since it's a vectorial, we have something more complicated. It's related to the polarization. So you see that, for example, you have T modes and TM modes, that in electronics, you don't have this. Okay, so you have more things in photonics because you have the vectorial nature of the photonic modes. But then also there's another different nature in electric band structure. You can define that we call the Fermi level. Remember, the Fermi level is the energy up to this energy that electric bands will be filled by electrons. Because electrons are fermionic particles and they follow the fermionic distribution, and you can define the Fermi levels. And then you define the conduction band and the valence band. But for the photonic band structure, the photons are bosonic particles. You don't have this kind of Pauli exclusion law. That means you can put photons everywhere in every band. So you don't have these Fermi levels. You can populate whatever bands you want by simply putting a laser resonances here. Okay. So they are same but different. But then things that you learn in electric band structure, why they are so important, you know, that to make photonic electronic devices like diodes, a transistor, you need to know the materials to try to make heterostructure by matching the electric band structure. So the same thing in photonics. Very important, this photonic band structure will dictate all of photonic properties in photonic crystals. So the color of the butterfly, that I showed you before, is just an example. But then you can also tailor different properties, how light absorb, how light reflect, but also how light can be trapped inside the system, how you can enhance the density of states, so far so on, etc., etc. So you can see that these spaghetti diagrams is the real appearance of the photonic crystals. It's not the color. The color is one of the properties. But then the real properties, the real appearance, the real passport, I can say that because if you show me a photonic band structure system, I can predict every properties of this system. So it's like if you show to the police your passport, and he knows who you are, what is your name, where you are born, etc., etc. So the photonic band structure is the real appearance of the photonic crystals. And now how we can try to teach new tricks, to try to obtain, to engineer this photonic band structure and to make new properties. It will be the heart of my talk today. Another features that's very related to the photonic system is losses. Because unlike electronic counterparts, photonic states are exposed to losses. So if you want to measure light coming from your system, you put a detector here. So what we measure actually is light escaping from your system. Even the laser point, the laser, you see the laser pointer, what we have on the screen is like escaping from a photonic cavity. If you want to inject particles in the system by optical pumping, I think the system is not a closed system, it's open system exposed to losses, and you pump the system through the losses. So the losses sometimes is bad, but sometimes it's important, but it's the native nature of most of photonic modes. Then the losses, how it you can see in the resonances is actually the line width of resonances. So if you perform, for example, transmission, reflectivity, or photoresistance measurements, you obtain the spectra. Then the line width of the spectrum give you the losses, and the position of the peaks give you the energy. With these two quantities, we can redefine the energy of the photonic resonance. Actually can be defined as a complex number. The real part corresponds to the oscillation frequency of light, and the imaginary part related to losses. So if you, for example, if you plot exponential decay, exponential EIET of this, then you have this guy is oscillation. And this, because you have the I here multiplied by the I outside, become the minus, and it will be exponential decay. It's like a pendulum that is oscillating but decay in time. So the decay time is by this term, and the oscillation frequency is this guy. So in this talk, we'll try to answer the following question: how to tailor on-demand complex photonic band structure to make novel photonic functionalities and devices. For the first part, we will focus on the real part of the dispersions, how to change the shape of the spaghetti diagrams that I showed you before. Okay, this is energy versus momentum. So again, we don't invent something completely new. We will try to learn things that we already know during our study. So during my study, my textbook, one of my favorite textbook of solid state physics is Assoc and Nguyen. So I think most of you also learn solid states through this textbook. So in the Assoc and Nguyen, there is a chapter to explain how the band structure in a solid state system originated from, and the explanation is based on what we call nearly free electrons approximation. So it means that the free electrons, the dispersion is a parabola, because it's energy equal to h bar square k square divided by 2m. So it's a parabola particle, and the curvature of the parabola is the mass of electrons. Okay. Then the solid states put on top of this free electrons some kind of periodic potential, a weak periodic potential. So due to the periodic potential, the first thing happened is we call the backscattering. So the parabola can be shifted with the quantity related to the Lorentz zone size of the block vector, and this momentum is calculated, so for example, by 2 pi divided by a, where a is the period of the potential. Then before you have the parabola, when they can shift it and duplicate it a lot of times due to the backscattering, you have crossing point. Okay? So it's the crossing point section between a positive group velocity and the negative group velocity of the free electrons propagation. And at this crossing point, when the potential is real, there will be a gap opening. So this is, and then you obtain the band structure. So while you have the crossing point, at the backscattering is there, you have the band opening. So the band crossing becomes band anti-crossing, and you make this kind of parabola. Okay, so we know this from our solid state lectures. We try to use it to explain and then engineer our photonic band structure. So the idea is the following. Okay, we need, in the electronic system, we have the free electrons. How we can have some kind of equivalence of free electrons in photonics? is a planar waveguide. Okay, the planar waveguide is a material with a thickness smaller than the wavelength, but then and the reflective index higher than the reflective index of the outside. So due to total reflection, light will be perfectly confined within this planar waveguide to make analogy of 2D electron gases. Okay, and we can consider our photonic crystals. Is for example, here I just show you 1D photonic crystals. You have the period only along x direction with the period a smaller than the wavelength. These photonic crystals can be considered like a perturbation of the planar waveguide, and the perturbation here is some kind of periodic perturbation that we put on top. So the confinement of the light and the propagation of light in this planar waveguide is something we can solve easily and analytically by just solving the Maxwell equation. So it's something we teach our students also in the guide optics. Then there are different guided modes. Each guided mode corresponds to the polarization and also how the electric field is confined within this slot. But here I just plot the fundamental guided mode. In the fundamental guided modes, light can propagate either forward or backward. So the group velocity is either positive or negative. So I forgot to remind you that the group velocity is defined by the derivative of the energy versus the in-plane wave vector. So here you have the positive slope, so the group velocity is positive. And here's a negative slope, so the group velocity is negative. And in guide optics, we have also a very important notion that we call the light cone. So the light cone, by definition, is a cone in the dispersion diagram, energy versus momentum, is defined by this simple relation. So the slope of the light cones is given by the speed of light. So that's why it's called the light cone. If you have the dispersion below the light cone, then photonic modes will be perfectly confined within the structure. It's totally reflected. It's called this region, the white region corresponds to the guided optics or integrated optics. But if you have photonic modes above the light cones, which is not the case that I brought here, then light can emit it outside, escape it from the structure and exhibit losses. Okay? So in the planar waveguide, there is no losses. Everything is below the light cone. And this dispersion, I don't show you here how we calculate it, but this can be calculated by solving the Maxwell equation. Then we have the perturbation, the periodic perturbation. The forward and backwards modes will be shifted by vectors, a multiple of 2 pi over a. So you have here 2 pi over a, here is minus 2 pi over a. You can see now my backward, when it's shifted, it can cross with a forward at pi over a at 0 angle. So it's high symmetry point. We call this X point, it is a gamma point. So you have different crossing point when we perform this perturbation. And of course, it's the same thing like for electronics waves. When you have crossing points, propagate and counter-propagating waves can interact and open band gaps. So yeah, the band gaps is 2U is due to the interaction between the forward and backward waves. So we have different band gaps. As I show you, you have the first band gap, which are below the light cones, but then most are also folded and are brought above the light cones. So the second band gap is above the light cones. So for the moment, I will focus on the modes below the light cone. So there is no losses. So when there's no losses, it's like the energy of the system is real. There's no imaginary part related to losses. We call this Hermitian system. So again, why is Hermitian? What is non-Hermitian Hermitian? You remember where in our quantum mechanics lecture, every operators need to be Hermitian because eigenvalues that we measure are real number. So when you are in a Hermitian system, then the quantities are real. Here we have no losses, so the energy is real. So energy is real, then the energy operator, the Hamiltonian, is a Hermitian Hamiltonian. Okay, I will spend time much in this kind of very calculation and theoretical part, but this will be one of the few matrix that I wrote. But basically, you can see the coupling between the forward and backward mode is dictated by a 2x2 operator, 2x2 matrix. So the diagonal part is uncoupled energy. So we have positive root velocity omega 0 plus VKX and negative root velocity omega 0 minus VKX. So plus VKX is a forward mode, minus VKX is a backward mode. And these two are coupled in the anti-diagonal part by the coupling strength U. So by diagonalizing this Hamiltonian, you can obtain actually the eigenmodes, so the energy of the lower and upper bands. So this is what we obtain here by can calculate the Hamiltonian and diagonalize it. So we obtain two parabola. Okay. The gap is given by U, actually 2U, and the curvature, actually the effective mass is given by U and the group velocity. And then it works perfectly if you compare it with the numerical simulation. You see that the effective Hamiltonian is perfectly reproduced in the numerical simulation. So our very simplified model learning from solid state physics works nicely. But then, of course, we can only have two bands, two parabola. One can think this guy is like conduction band, this is like valence band, but for photons, but that's it. Now the question is if we can do something more interesting based on this method. Think of your dispersion like spaghetti. Then if you want to change the shape of your spaghetti, you need to make your spaghetti interacting with each other, then they can repelling, and then change shape. So what we already did before that they have like this positive group velocity spaghetti, this negative group velocity spaghetti, they interact with each other, repelling, and they make this kind of band gap. But if you want to make more complicated things, we need more spaghetti coupling. We need more modes. So look at the photonic crystal. Okay. So what I showed you before is just the fundamental mode. So the propagative and counterpropagative coupling open the band gap. Is the red modes here. So the fundamental modes, that means the vertical confinement is even modes. It's like the quantum realm. You have the fundamental modes. It's at the maximum of the field is at the middle of the confinement. Then you can also have the first excited modes. Here you have the second band gaps, the two blue ones. So they are now odd parity. You instead of having the maximum of the field in the middle, you have the minimum of the field in the middle. So this one is a symmetric function. This one is anti-symmetric function. And symmetric, anti-symmetric are not compatible. So the two dispersion, the red and the blue, cross each other without any coupling. And you want to make our spaghetti coupling. When to put the coupling possible. So the way to go is to break the vertical symmetry. So for example, instead of etching through completely my photonic crystal, I let a little bit slabs still exist here. Then I still have the modes A and B. Yeah, is odd like and even like, but they are not perfectly odd, perfectly even anymore. So that they can couple to each other and open the gap in C and D. So the crossing point here becomes the anti-crossing. And if you look at the wave function of the field at C and D, you see that is especially something like hybrid, 50% of A and 50% of B. Okay. So by hybridization of the modes of the odd and even by vertical symmetry breaking, I can make some kind of W shape and M shape dispersion that before I only have parabola dispersion. So this concept is that, okay, we can make spaghetti coupling repelling by breaking the vertical symmetry. And then you can change the spaghetti shape by changing how we break the vertical symmetry. So how the symmetry is very broken or a little bit broken. So this was the idea that we do our experimental demonstration. So we fabricate the sample is for the crystals with the vertical symmetry broken. So the sample was made from silicon. The vertical symmetry is broken because we don't etch completely, and also it's sitting on a substrate. Sorry. And how we tune the vertical symmetry breaking. So of course, one of the ideas is to change how we etch the system, how deep this etching is. But then you need to fabricate different sample, each sample with a different etching depth, and it's not easy to do. So what we did in this experiment that we keep the etching depth constant, but we change the ratio aspect of the photocrystal, this FF number. So by changing this, we can change finally the vertical symmetry breaking. And this is experimental measurements. Each measurements correspond to the reflectivity as mapped as a function of the in-plane wave vector, and here is the energy. So when you see the resonances, they are different photonic band structure. But by changing the fringe fraction, you can see that we tune continuously a photonic band structure from two linear dispersion coupling one to the other one. It's a direct cones. It's like the dispersion of the K and K prime is a graphene. Remember? So it's two touching with linear dispersion. And then you open the small band gap, you make two parabola. And if you change again the fringe fraction, you can even make flat band, completely flat. You see that the dispersion is a dispersionless. There's no change in the dispersion as a function of angle. Of course, it is a local flat band because if you go to higher wave vector or higher angle, then the band is not flat anymore. The lower band is an M-shaped dispersion. So these are experimental measurements. And we perform the numerical simulation to check that what we measure is correct or not. And actually, you reproduce perfectly what we measure here. And putting on top the red colors are the theoretical prediction. So by simply using the symmetry breaking, we can change the dispersion from zero effective mass, linear dispersion, to infinite effective mass, very heavy photons, flat band. So this is a concept that we can change the dispersion like we want. How we can implement it into some real applications. One of the applications is that if you have flat band, you enhance the density of state of light, and then you can enhance light emission if you put active material inside the system. I forgot just to show you, yes, what has been shown before. It just is the reflectivity map. But then sometimes people have the habit to see at the spectrum. So every vertical lines here, you can extract it's like a spectrum. So for the direct cones, you have here different spectrum when you change the angle. And if you follow the resonances, you have the direct dispersion. And for the flat band, if you change the angle, you see that the resonance stay the same. So it's a flat band dispersion. Okay. So our first application is to enhance light emission by using all of this kind of nice dispersion effect. So again, we keep our sample with the silicon. So silicon is very well known to be bad in terms of emitters, because silicon with all of the perfect properties for electronics are very bad emitters, since silicon's an indirect semiconductor. So electrons and holes reactive recombination is very bad. So we use it as a test bed. Okay, it's bad, but then if you show that you can enhance something bad into something which is acceptable, then your concept works. So we take a piece of the silicon, you perform the measurements, photoluminescence measurements, you see, okay, the signal is, you see a little bit signal, but it's very low. And this signal depends on angle because the silicon slab makes some kind of bad ferrite cavity. But then when we pattern the silicon into our photonic crystal, here we call the meta surface. It's another kind of calling the system, because now we are in the metaverse, and people want to call everything meta. So we have something we man-made, so it's a meta structure, but basically still is our photonic crystal. And we perform the photoluminescence. You see that the resonances are very well defined. And when you have the resonances, where emission is enhanced, and the enhanced, like 2 order of magnitudes. You take this guy, you divide by this guy, you have the enhancement in log scale. And you can see, okay, where you have the photonic resonances, this way photoluminescence is enhanced. And it enhances, especially when you are close to the low curvature, where the band is flat. So here, for example, you have very red emission because the band is almost flat. Here's another way of presenting things. So you see the intensity is the z-axis, and here you have the kx and energy. So you can see, okay, when you have the almost flat band, then emission is very strong because the density is high. When it's a linear dispersion, it's not very high. Then when you have the curvature, zero curvature, then you enhance. So we can tailoring the density of state in the Fourier space at will. The Fourier space is a momentum space, and you use it to enhance the emission where we want it. Another application that our work perform is how to increase what we call the downshifting enhancement for solar cells applications. So, you know, basically solar cells is you have sunlight shining on your solar cells and convert into current. But the conversion usually lost in the UV range, because in the UV range, most of the photons energies is served for heating the solar cells, increase the temperature of solar cells. So one of the solutions is to recover these losses by converting the UV photons into visible photons by putting what we call the downshifting layer. So we can think of the downshifting layer that, okay, sunlight shining on top here. Most of the sunlight will be pass through this downshifting layer and go to the solar cell, except the UV light will be absorbed and then re-emitted into direct emission. That is very good for the solar cells. So it's actually the idea of this downshifting layer is that the downshifting layer absorb blue light, so where the solar cell efficiency is bad, and then emit red light where the solar cell efficiency is good. Okay. So we need to make a good downshifting layer, and our idea to make a good downshifting layer is to make it, we call this photonic crystals, the transparent photonic crystals that can enhance absorption in the blue and enhance emission in the red. Okay. So this is the demonstrator. You can see our downshifting layer is completely transparent. What is on top of this layer is a photonic crystal made of silicon nitride and yttrium oxide doped with europium. This is some kind of rare earth material used like our downshifting layer. And in order to enhance the downshifting properties, we put it also a silicon nitride photonic crystal. So together we have our vertical symmetry breakings photonic crystals. A little bit different that here in order to make it optimized, instead of making 1D photonic crystals, it's a 2D photonic crystal. So instead of having like grating, we have whole lattices. The period is about 250 nanometer. Okay, so my PhD student at that time is also a Vietnamese one, Vu. He did a brilliant job by making the photonic crystal on the whole size sample, 1 centimeter square, by what we call the techniques interferential lithography. So to make these small pitches whole for the whole sample. And you can see from the SEM measurements, we make some histogram, and you can see that the whole radius is very homogeneous, even within 1 millimeter square. Okay, so these are the sample, and the sample was designed to make flat band in the UV and the blue, 400 and 420 nanometers. So this is what we measure, and this is what is simulated. Okay, we measure here, since we have the square like this, we have two directions, the gamma X and gamma M. So the angle is measured along gamma X and gamma M. So in gamma X, this is a flat band. And this flat band in the blue, it's a slow light, allow us to enhance absorption. So we measure the absorption in the reference is almost zero, it's very low absorption. And when you put on the photocrystals, absorption in the blue is enhanced by 25 times. So it's well reproduced by the simulation. So we trap, we perform light trapping at in the blue. So since it's a slow light, so photons are slow down, and then has more chance to be absorbed in this wavelength. So we enhance it in the blue, but also we want to enhance also in the red for the emission. So it's the work, the downshifting layer work in the transmission scheme. So we want to look, the blue light will be converted into the red light. Okay, red light is 611 nanometer, and we perform also the angular measurements of the emission. So you see here it's there. When you have the photocrystals and when you don't have the photocrystals, the emission 611 is very low and is not depend on the angle. Okay? But then when you put on the photocrystals, you can see a lot of lines here. Each line is corresponding to different emission lines of the Earth, and when it's crossed the photonic modes, yes, it perform. You have the resonances, and so light is much better extracted through the photonic modes. What we measure in the end, and we integrate the emission with the presence of the metasurface, we have the downshifting enhancements of 77 times. And this enhancement is involving both absorption and extraction mechanisms. Okay, so I think I convinced you that by using a simple photonic crystal layer, we can engineer the real part of the free dispersion and then detect how light interact with matters to make light emission enhanced or absorption enhanced for different kind of applications. We still stay in the real part, how the shape of our spaghetti, but the question is how we can go farther. The idea of how we can go farther is in our group, we think of also is something we learned from the solid states. I mentioned you later. So use more than one photonic crystals. So we talk about more interesting feature with multi-layered photonic crystals. In France, when you think about multi-layer, there's a very famous example that is the millefeuille cakes. Millefeuille cakes, you see this one is a cake with different layer 1, 2, 3, 4, and they are not separated. They stick one to the other one by some kind of creamy, then it's just creamy layer here. So we cannot think of a millefeuille cake like different cake. The whole is a cake, and you eat it like a whole, and then the fact that you have different layers sticking to the other one plays a very important role. So our multi-layer photonic crystals idea is based on this concept. So we suggest to use a different photonic crystal layer, one on top of the other one. We see the sub-wavelength period, that means the distance between two rod tiers is smaller than the wavelength of light. But then, like a millefeuille, we need that they interact with each other. So the interdistance between layer are also smaller than the wavelength. So sub-wavelength period, sub-wavelength interlayer distance. So basically, light confined in a layer now can leak to the other layer. We will have two mechanisms. Intralayer couplings that I showed you before, when propagating light and counter-propagating light coupled by the coupling strength U. But then also propagating light in one layer can couple to propagating light in the other layer via evanescence coupling or interlayer coupling. In this talk, we will focus only on the case of bilayer photonic crystals. So we have only 2 layers. And we will see how we can engineer the photon dispersion of these. So I did different kind of works on this dispersion engineering, but today I will only mention about how we engineer it with the Mori patterns. So again, the Mori patterns is a French word, but it's also now is international words. Is first the visual patterns that it form when you have 2 opaque and transparent layer overlaps. You can see that here you have 2 ratings with slightly different periods, and here you have 2 lattices, and you rotate it. You see that new patterns emerge. From the small pattern at the beginning, you have like new bigger patterns emerge. And these bigger patterns, the super patterns, are called Mori patterns. You observe also here in real life. Okay. So why Mori patterns is interesting, and what we can obtain from the dispersion engineering of the Mori patterns for the crystals. If you look at Mori patterns in physics, I take the abstract of physics propagation starting from the 2020, you can see the citation at the beginning is not a lot, but then it's like a lazy curve. About 2010, there is this first threshold is actually when people studying the Mori patterns, when you put one graphene layer on top of the other one and you twist it. What we call the famous twisted bilayer graphene that is very trendy now, and there are this famous paper now becomes very seminal, show that when you twist bilayer graphene, you can create a flat bands. Knowing that graphene at the beginning is a direct dispersion for electrons, when you twist this, now this paper suggests that you have flat bands at some magic distance, that you cannot twist it for every angle. At some angle, it becomes the flat bands. So it's attract a lot of interest. And then in 2016, 17, you have another threshold. Nowadays become quite crazy because people observe that at this flat band configuration, or called the magic angle configuration, you can obtain like many body physics, for example, unconventional superconductivity, and then the beginning of the twistronics. So the flat band, something related to dispersion, can be engineered from the Mori structure of electronics system or solid state system. We try to mimic the same thing for photonics. But first, just to illustrate again how these Mori features look like in the twisted bilayer graphene. So we have 2 graphene, layer 1 on top of the other one. Then you twist this as a function of angle. You'll see that the Mori patterns emerge. And then if you calculate the band structure of electrons in this twisted bilayer graphene, you see that at some magic angle, here, the direct dispersions become completely flat. And it's not like a local flat band like I showed you before in my single photon crystals. The flat band is for the whole Brillouin zones. And it only takes place at the very specific angle. That's called the magic angles. So we try to do the same thing with our platform. And of course, we can make a honeycomb lattices for the crystals and then twist it and look for the magic angles, but for photonic system, like a lot of groups do. But then say, okay, then we just copy things already exist. What is better is that we can learn from them and do new things in our ways. Since for electric system, they already have graphene, so they cannot make other kind of patterns. In photonic system, we can do whatever we want by just patterning, by using e-beam lithography or other kind of lithography and then etching. So we propose, instead of using twist layer of 2D photonic crystals, we use 2 gratings, 2 photonic crystals, 1D photonic crystals, but with slightly different period, one on top of the other one. So you see the blue photonic crystal here has a different period than the red one, the bottoms. So when the 2 periods are slightly different, you can observe this Mori pattern emerge. So basically, the real system is the following. We have two photonic crystals, one on the top of the other one. The period is slightly different. Then if the ratio of the periods is not a rational number, we will have a lot of issue. We will be in the quasi-crystal system, and we want to stay in the photonic crystal system. So we make sure that you can define a periodic system. The ratio between A1 and A2 should be a rational number. In our case, A1 and A2 is defined by n divided by n plus 1. That means n plus 1 period of the upper layer is the same like n period of the lower layer. Here, n is a natural number, can be 2, 3, 4, 5, 6, 7, etc. And we want to consider the case of n is big enough so that the two periods are very close. Okay? So again, we stick in our favorite system, the silicon system that we know very well in our lab. The period is chosen about 300 nanometer, and the thickness is about 180 nanometer. So all of these are much smaller than the wavelength, the telecom range, 1.5 micrometer. So how photonics most will be built in this, or how light in travel and exist in this kind of systems? So I remind you what we have seen before, that for each layer we have like forward and backward lights that are coupled to this backscattering mechanism. So it's coupling strength U. Below, so forward, backward, coupling U. So U is the interlayer coupling strength and can be engineered by changing the filling fraction, the ratio FF here. Then the forward and backward modes of each layer can couple to the forward and backward modes of the other layers by the coupling strength V when the distance L is small enough. This is by some kind of evanescence coupling. So by changing the distance between the two layers, we can changing the interlayer coupling V. So I just show directly for the results. We perform the numerical simulation when changing the distance between the two layers. And here are the theoretical calculations. Okay? So by changing the distance, at some point, we obtain perfect flat bands for the whole mirroring zone. So it's also very well observed in the calculations. So when you change the distance, most of the time you have like just band with dispersive bands, but for some magic distance, the band become perfectly flat for the whole mirroring zones. So it's very similar to the magic angles, but for twist-layer graphene. Here we don't have the angle exchange. What we change here is the distance between the two layers. And you remember that for each Morey pattern, is dictated by the number n, and is the number of the size of the Morey pattern, or the number of the upper period and the lower period with respect to the other one. Okay, this one. So for each n number, we have a different Morey pattern. Then we scan the distance, and what we plot here is the bandwidth of the free band. And for some specific distance, the bandwidth is 0. So it's a perfect flat band, and it's very well reproduced by the theory. So the number of magic distance depend on the Morey pattern number n when intralayer coupling is fixed. And we have here a very nice concept of magic configuration in photonics that is directly inspired from the magic configuration in electronics. So before going further, just conclude from this first part of the real part dispersion. I hope that I convince you about how we can engineer photonic band structure in single and multi-layer photonic crystals, and we can make it really on demand by coupling modes, by making our spaghetti curve repelling, interacting with each other to make flat band, direct, and multi-valley dispersions. So before going further, I don't know, maybe we can stop here for questions on this part. then make also some kind of stop. So if you have question on this, please go ahead, or I can go for my second part.
So anyone want to have a question now and discussion with Professor Sơn?
Thanks. If you don't mind, may I ask a quick question, please?
Yes. Hi, Chung.
Yeah, hi, sir. Yes, good to hear you. So I have very naive question. You know, I'm outsider. So my question is regarding the part where you show application with solar cell, where you absorb not really solar cell, but for the where you absorb 400 nanometer and you emit 600 nanometer light.
Yeah.
In that part, can you briefly explain to me? So how does it work with conservation of energy?
Here you lose energy because one photons in the blue become one photons in the red.
But it means that this 400 nanometer is like electronically absorbed by this material, right?
Yes. So actually, this 400 nanometer photons is absorbed by we call dark shifting layer, and this dark shifting layer convert this into the red photons with very good efficiency. But then at least the solar cell can use these red photons, because the blue photons is useless for solar cell. So this is this idea.
Okay. So, but then it means that what you are working also, so it is a kind of a top layer above the electronic absorption of this particular material.
Yes,
right?
Yes,
because
yes.
If this material doesn't have electronic absorption here, then your photonic band structure would not be working, right?
Yes, absolutely true. So here my materials really need to be able to absorb the blue light. That's why this item material that people use for downshifting, because this material is very famous to be able to absorb the blue light. Not very good absorber, but then the efficiency to emit the red light once the blue light absorbed is very good. You have almost
improved by your technique.
Yes, and then but then the absorption is very low, so that's why we need to improve. You see that the absorption here is, you see the zero, the absorption in the red curve is almost zero. But then with my structure, I enhance the absorption.
Very good, very good, very good. Thank you.
You're welcome.
So then what the total efficiency you can compare with and without the structure, right?
Yeah, you need to put on the real solar cells. That's true.
Yes, and what do you have the final answer on that yet, or?
No, because actually what happens is that if you take a commercial solar cell, they are already optimized, working without this guy. So if I want to you see all of the cover things, you have the glass and all this pattern. So if I want to implementing this on the real solar cell and have some real good effect, I need also to re-optimize the solar cell, and these things we don't do. I mean, we need to hook up in an industry who make the solar cells to do this. So this is just a concept that how we can make this kind of transparent layer. It's really transparent. See here, but that's then
very nice.
Yes, yeah.
Thank you.
Okay, thank you. Maybe Florian, you write the hand first.
Thank you. Thank you, Aisen, for this presentation. It triggered a lot of memories. So
yes, you see, a lot of your works is here.
So I would have some question on the end of your presentation on the moiré lattice and the flat band structure. If I have time, maybe I have two questions, but the first one is very short. So if I understand well, the number of this flat band position depend on this n number.
Yes.
Is there a minimum number where this flat band cannot be exhibited at all?
So here we have 3 parameters. The interlayer coupling strength is V, the intralayer coupling strength U, and N representing the moire. I didn't have time, but in the paper we managed to make an empirical relationship between N, U, and V for magic configuration. This is like how many magic configuration we have, depending on N and also on U and V. So basically, if your layer are very far from each other, L equal to bigger than the wavelength, then whatever N or whatever U, you cannot make flat band. So it's U, V, and also the N together. The 3 parameters interplay between the 3 parameters make you the flat band. So it's yes. So for a given N, if you don't have good V or U, you cannot make the flat band. I don't know if it's answer the questions.
Yeah, perfect. Actually, it was answer my next question, where I was interested to know if there were actually a relationship from the modeling that could give know exactly which can trigger this flat band. So thank you very much.
Thank you, Prof. Please, Nguyen.
Yeah, thank you, Andy. Thank you, Anson, for very interesting seminar. And I take care of baby at the same time. So sometimes I focus, sometimes I lose focus. But I ask question, and if it's not correct, so please correct me. So I would like to ask about the downshifting enhancement.
Yes.
So that you can enhance the absorption property of the material, right?
Yeah.
Then what about the emission and scattering? Do you also enhance emission and scattering?
Yes. So here if you look at the modes in the blue, you see that absorption is enhanced, and the enhancement in the blue is because we put photonic resonances in the blue, and these photonic resonances depend on the angle, so we use a band structure, and we make it a slow line mode, so photons are slowed down and then absorbed in the blue. But for the red, we also engineer so that you have photonic resonance in the red, and you can see that all of these lines are the emission spectrum of our material. So when the emission spectrum, when it crosses, the resonance is enhanced. This is not a pulsar effect, but it's more like how we direct light emitting in the good direction. It's some kind of antenna effect. You can see, but the collective antenna effect. So we see, so we see a scattering or the extraction effect.
It is connected to the interference. Used to the interference, so it's enhanced.
Yes, because periodic structure of photonic crystals behavior, the modes here are based on interference of light. So you can say that as well. So by every emission, in general, you have emission in every direction, and also emitted inside the sample and cannot escape. Light cannot escape. So a part of light cannot escape. But then by making this interference feature happens, we can redirect photon emitted into a good angle.
Yeah. So may I ask you, so please give a comment on, now you try to make a pattern on the sample. What happens if we make the pattern using light? I mean, we can make the interference of the light and shine the interference on the surface of the sample. Do you think the effect will be similar?
I see that instead of making the pattern, I pattern the incident light, right? Is your question?
Yeah, we make the interference on the surface of the material. So then maybe it should be similar, or?
Yes, but then you don't, I mean, you lose your emitters, right? Because you only excite a part of your emitters, and also it's very difficult to make to make a good interference feature at the subwavelength scale with high intensity, because basically what everything we measure here, the pump spot is very small, about few microns. I don't know if you can make an interference features which is small and intense and with a small period, but the idea is very attractive. Yes, I think you can do a lot of nice things with this, in my opinion.
Yeah, because it's connected to what method I see is it's called the interference enhanced Raman spectroscopy. So by changing the layer of the substrate and the laser of the sample, they can make the interference between the incident light and the scatter light. So they have an interference pattern on the sample, and it makes the enhance the scattering photon. So it just connected. So
yeah,
I'm thinking about that.
Yes, sure. So it's very nice, because it will connect at some point at my next part of the talk. But then just to be sure that here the interference is between different emission part of the sample, because the incident excitation is in the blue. You can see that, and the emission is the red. But the different point of the sample will emit red light, and then it will interfere with each other. So there's no interference between the incidence light, the blue, and the red. Yeah, but the idea is very similar.
Thank you very much.
Thank you, Nguyen. So, Thang, please.
Thank you very much. Excellent talk. I'd like to become a PhD to follow the own topic you are working now. Really, yeah, amazing topic. Actually, I'm working with Florian. So when I received the email from Nguyen about the talk, I was really excited. And last week talk with Florian, I'm going to give a talk. And yeah, we have been talking about you for a long time. I was at the Institute of Physics before, and yeah, several times attend your talk. Also, I was also working with Tailors for a few months on yeah, strong correlated system, but yeah, never quantum dot interacted with light, and sometimes yeah, we met, but yeah, it was quite a long time ago. Thank you very much for this interesting talk. Come back to the talk. I have two questions. First, about this, you mentioned this, yeah, about this engineering loss or tailoring loss from metal structure. So it talk about the loss here is mainly the loss due to scattering or kind of like absorptive, or also you consider to put also the intrinsic loss of the material into the devices.
Yes. So yeah, thank you for the question. So actually, this first part of my talk, there is losses, but it's not the losses that I will engineer later. So here the losses is almost negligible. You can see, for example, in my first example here, I go back to it again. Without my photonic structure, the absorption is almost zero. So the system is very low losses, and my photonic modes allow to enhance absorption, but the losses is still very low. And then everything here is mainly due to the real part of dispersion, the shape of dispersion. For example, here is because the dispersion it's flat. So the next part of my talk, I will more focus on the losses, and the losses that I will mention is actually because photons can escape out of the system. So it's not an intrinsic loss of the material. Every material that I use in my presentation here is almost lossless, but it's basically because photons can escape out of lossless material to go into the free space, and this is the radiative losses. Yeah. We will just mention this later in the second part.
Thank you very much. And about this for the for solar cell applications, it is very nice that you can really convert light from UV to the visible regions to enhance the absorption efficiency of the solar cell panel. But have you considered in total efficiency of the solar cell, even though when we convert it from emission from absorption from UV to the visible, have you considered the total efficiency after the conversion? How much compared to the intrinsic solar cell? Because look at here, for example, the absorption of the solar cell in the UV range is not so bad, but when we move it to the visible range, consider the quantum efficiency of the we call it like a diode absorber, which is observe UV and emit visible, and how its efficiency in reality can be enhanced.
Yes. So thanks to very good question. First, you are right that nowadays it's important if you want to make a real game changer in the solar cell system is to see how all of this, we can say, third generation concept solar cells can improve the solar cells efficiency. All of the conversion layer, either up conversion layer or down shifting layer, down conversion layers, the problems of them is that they only play in a very small spectrum range. So you can see here that the emission is like very sharp at 600 nanometer. So if you improve the very small spectrum range. So integration of this is small, and you need to think about the price to pay. Okay, the first price to pay is the parasitic absorption that you put due to the presence of the downshifting layer. Even that the downshifting layer that I use here have the almost 100% quantum efficiency. That means that you absorb 1 photon in the blue, is guaranteed that you have 1 photon in the red emitted. So this is 1-to-1. But then how the photon in the red emission is used is another question. So it's if it will be losses or if you emit it into the solar cell, and the whole thing is to be take into account the solar cell's structure. So to my knowledge, nowadays all of the up conversion or down conversion, down shifting mechanism didn't make any real change in the solar cell technology. So it's what we do here is just a proof of concept. I mean, the photonic concept. Say we want to improve this, and the motivation is for solar cell technology. But yes, it's more like a fundamental concept and real device applications. We don't. At that time, we start thinking about how it's changing the real solar cell, and we see that there are a lot of parameters that we don't control, and we cannot really say that we can make a difference or not, because the real difference may be very, very tiny. So it's a very good questions. Thank you.
Thank you, sir. I could have some other questions, but I would give the time to other colleagues to ask. Thank you. We still have time. I would like to discuss further with you on several topics that you are working on.
Yes, and also, of course, if people want to discuss with me later or even do collaboration, I'm very open.
Looking forward. Thanks.
Thank you very much, Thắng. So let's invite Professor Tuấn from USA, because it's very late in US now. So please, Tuấn.
Yeah, thank you. It's very, very nice talk. Yeah, I enjoy it, and it's simple enough to understand. But
thank you very much.
Still something I don't understand. Of course, I'm not in this field. So can you explain how do you measure the dispersion of the nanocrystal of the photonic crystal?
Okay, so this is very good questions. That's actually the question that most of my students ask me when they start PhD. How you measure this? So basically, the dispersions is energy and momentum, but the momentum is related to the angle. I have the relation at the beginning.
What I mean is that in measurement, how do you change the angle? You just move the detector, or you change the sample?
No, if you do this, it will be very bothersome, because you need to do angle by angle, and then it's very difficult to stay on the same spot because our structure is very small. What we do is Fourier spectroscopy. So basically, you take a camera like this one. You take a picture, then you take the picture on the sensor. Is a real image. So XY in the real life become XY on the sensor, right? But then I don't want XY. I want KX and KY. So I need to perform a Fourier transform. Fourier transform of light is something very easy because you use a lenses, a supplemental lenses. For example, you have a spot, you put a lens at the focal plane of the spot. Then after the lens, you have parallel beam. So you transfer something from the real space, localized, into something not localized in real space, but localized in K space. So with a lens, you can do the Fourier transform of light. So what we do here is to, instead of imaging X and Y, we image KX and KY on our sample. So, but then you still need a third parameter is a wavelength. So you have KX, KY, and wavelength. We have 3 parameters. And on the sensor, we only have 2 dimensions. So we need to sacrifice one of the 3. So what we sacrifice here is KX. So we use a slit. You know, on the spectrometer, you have an entrance slit. So the entrance slit, we select a given KX. And then you project it on the sensor at the end of the spectrometer. So on the sensor, the x-axis becomes the wavelength, and the y-axis is a wave vector, KY. So it's so it's basically like, imagine you have the parabolic dispersion. Okay, you cut vertically the parabolic dispersion paraboloid become a parabola. So so you and that's how we perform the dispersion measurement. Space is not very it's not very straightforward. If I can, I have just 1 minute, so I have.
I got it.
Yeah. So this is the basic idea of the measurements. I don't know if I have the. I don't have the experimental setup. Sorry, but just for your question, this picture is single shot measurements. It's like taking a picture.
So single shot measurement, you already got a deep person with the wavelength also.
Yes, yes.
And how long they take for the one measurement?
It 3 seconds.
Wow.
So I think I will show you some because if you have like a few minutes because I have this time ago. Yes, dispersion measurements. Yes, actually, it's the techniques that you asked before this. Either you change the angle of the sample, you change the angle of detectors, and it's very time consuming. So what we do is to do the Fourier transform of light. So it's Fourier transform of light is basically you use lenses. If you have localized in space, you have they localized in space after, but localized in K. So you can do the other Fourier transform. You have localized in K. You put the lenses, you become localized in space. So you can switch between K space and real space by just the lenses. So what we do is that we image the bifocal plane of the microscope objective on the camera. So you have Kx and Ky on the picture, but you don't have the information about the wavelength. So we'll put a spectrometer, it is a camera, and the slit of the spectrometer, select a given Kx, and then you split it. After the spectrometer, it becomes wavelength and Ky. This is the idea. And just show you, yes. You see, this is techniques with changing the angle. My PhD student, he did it for 2 hours. And this is 30 seconds because we enhance it a lot. And what is funny because the simulation itself takes like 10 hours to simulate. So we spend more time for the simulation than for the measurements. So this
I see.
Yeah.
So I was also wondering if Polaritron, right? You know Polaritron, right? It also you measure the same thing. And can we apply this technique into the Polaritron or not?
Yes, yes.
Because it looks like the photon is a dispersion angle. It's quite small compared to this one. This one, you can go to few degree, right? It is 10 degree. It is quite high.
The brightness is also very dispersive, right? You can go to 40 degrees in the brightness. Is that what kind of materials you are referring to for brightness?
Well, in general, I have no idea. Just in general.
Yes, this technique because we do also for brightness. So for brightness, you have like excitons and then photons dispersion. And when you make the brightness, you have also anti-crossing, very, very similar to this, but in the broader splitting. That's we use the same thing for brightness measurements.
Okay, very nice. So in those samples, there is also silicon nitride and europium 3 blood, right?
Yes.
Can you explain about the role of that in the measurement and in the observation or in emission? Is that europium is play a role there or not?
No, europium is a active layer. Is absorb and emit. So this is this guy is a guy who plays a downshifting material, and the silicon nitride layer has been chosen because silicon nitride has almost the same refractive index as europium. Is yttrium dioxide. So the whole things make the photonic results. And then the presence of silicon nitride, which is transparent, enhance absorption of the europium. Yeah.
Okay, so the absorption enhancement, it comes from the europium 3 blood, right? If you don't have the 3 bloods, and probably, or you change to different ion, it could be different. Is that?
Yes, yeah. So this one is one to absorb. So if you change the material, is not the same absorption anymore. But but the enhancement, the absorption is come from the silicon nitride.
Nice. And in the Mori pattern, do you also study the superconducting in that one or not?
No, because superconducting is for electronics states. So we are with photons. So we expect
with the Mori pattern Mori pattern in the bilayer graphene, right? When you make it the magic angle, and it becomes a superconducting. Is that you also study with that or not?
No, because we are working with photons, so we are not working with graphene. I just show graphene to say where our source of inspiration come from.
Okay, good. Thank you.
I just want to comment to
glasses look
more pattern.
Look nice.
I think this is a very interesting topic. Nguyen and India also working on this because you also use this kind of like nanosphere lithography. It kind of like opal structure, but when you might try to make a monolayer, and always some part you have like multi-layer, and normally the layer between them are really not well aligned, and it makes that kind of some more pattern. And for sure that's Nguyen. Also in depth, I saw one paper you also work on nanosphere lithography using such kind of either silica particle or something, some other particle, but the only way that we can really make such kind of more pattern just using multi-layer of the sphere. It's also quite interesting.
Yes, thank you.
Thank you. So
information.
Maybe Nguyen, please.
Thank you. Yeah. Hi. Thank you, Hai. So it's very nice. It's very nice talk. It's not only the presentation, it's like lecture showing us how to use the photonic to tune the emission or the absorption properties of materials. I really enjoyed your talk. And actually my work is related to yours. We work with photonics with phosphor materials like downshifting and upconversion, and we apply the photonics structure to improve the emission densities. We prepare the 1D photonic structure with the multi-layers, and we also try to pattern the structures, like to have the resonant match with the absorptions or emissions of the photon, and to improve the output. And it's not, not the question. I just want to ask you if we can have the individual meeting, that we can talk more details in our work and just, and maybe that we can have something we can collaborate, because my work is very similar to yours. We applied a lot of photonics to improve the photon emissions.
Sure. I will be more than happy if we can try to figure out something to do together. Yes, I think it's one of the main ideas this kind of exchange, right? Is to put the network and try to work together. Yes.
Nguyen, can you introduce yourself to on?
Yeah, I'm a postdoc in the Institute of Material Science of Civil, and it belongs to National Research Council Spain. And in our work, we have different working areas. We have working in photons, in the solar cells, and mostly we just playing with light. Like we're not with the solar cell. We're not only like to try to improve the emissions, improve the efficiency, but the main point here is that we also try to play the interaction with photons with materials, how to change the properties, how to improve the absorptions or the emissions. Yeah, that's our work. And then my personal work, I'm working in the upconversions. It's similar to yttrium oxide doped with europium, but we dope with another radon elements. And then instead of have convert the violet light to visible, we convert the infrared photons to visible.
So you work with erbium, right?
Also do the downshifting too. I mean, in our group we work cover this.
That is a conversion, no? It's not down
conversion. Yeah, conversion.
Yes, yeah.
And also realized one questions of Tuan Ching, that he asked about the measurements of the dispersions. We don't do this measurement, but we do the emissions of angular dependence measurement. Yeah. We're changing the angles, and we measure the emissions. But we change we put the samples and the detectors in the rotation state, and we're moving the angles. Experiment is really time consuming.
Yeah.
But we got very nice results. We show the emission time dependence in the photonic, because it shows the resonance dependence on the angles of incidence.
Okay, thank you very much, Nguyen. Maybe we let Hai-Sơn continue for maybe, I don't know how long, Hai-Sơn?
It will be shorter. I mean, it's really more conceptual, but I try to make it short. I like the discussion more than what I'm presenting, so I try to make it short.
Okay, I think that we have more question to you, so maybe you can for 15, 20 minutes, and then we have a more discussion. Okay.
Sure.
Please continue.
Okay. So now we go to the lossy wall, and we try to take into account the losses. And when you have losses, we are not dealing with the real energy anymore, but the real and the imaginary part of the energy. So we talk about complex photon dispersion. So just go back to the scheme that we started before. I try to make the pointer. Yes. So in the first part of my talk, I focus onto the first band gap of the photonic crystals, which is below the light cone, so it's protected from the losses. And we talk about Hermitian Hamiltonians given by this matrix. In the second part of my talk, I will focus on the second band gap. So this one is also opening when the forward and backwards are coupled. through the periodic patterning. So the gap opening is 2U given by this coupling. But then now this modes is above the light cone. It's inside, unless it's inside the light cone. So photons is not confined perfectly anymore in the waveguide, but then can escape outside to couple with how we so-called radiative continuums. What does this mean, radiative continuum? Is like even in the vacuum, you have possible electromagnetic waves. So it's so from the outside, every electromagnetic waves can exist. So it's a continuum. So we know already some very nice effect from this radiative continuum. For example, the so-called Casimir effect, when you have the forces coming from the vacuum, but actually it's not the vacuum because this vacuum is the host of the continuums of waves. So photons, every photons inside the structure, when it's above the light cone, can link to the radiative continuum. And then the system is not a conservative system anymore because you need to take into losses and become the non-emission. So I won't say much about this non-emission physics, but what I will highlight is we can also engineer the losses by interference features that people call the Friedrich-Wingant interference. So what is a Friedrich-Wingant interference? You have two resonances, omega 1 and omega 2, couple one together, one with coupling strength U. Then each of resonance lead to the outside, gamma 1 and gamma 2, to the radiative channel. In the Hamiltonian description, you have the first Hamiltonian is a coupling between omega 1 and omega 2 by U. Okay, this is the one that we saw before. Then in the seminal paper from Friedrich-Wingant in 85, they suggest that the two resonances will link to the continuums. Okay, so then you can write in the diagonal part the two leaky channels, gamma 1 and gamma 2 is the imaginary part because I put the imaginary number here. But more than that, they can crosstalk to each other through the radiative channels. So the crosstalk is you can couple also the two resonances via the losses. So it's given by this square root of gamma 1 and gamma 2. You can basically think if this radiative channel is like the road. Okay, you have two houses. People from this house go to work, so they need to take the car and go to the road. This family also, the father needs to take the car and go to the road. And maybe when they go to the road together, they can see each other on the road and change their life because they meet each other. So it's this kind of coupling via the losses. So if you don't have these losses, then people will say in their house, and the only way to coupling is when the two houses are very close one to the other one. This is a basic scheme of the Friedrich-Wingant, is that with the losses, you can also make the coupling through losses. And this is very interesting because I won't go into detail, but you can make some kind of special configuration that you make the destructive interference happens. So at the beginning, you have two resonators, one with losses gamma 1, the other one is losses gamma 2. You take into account the Friedrich-Wingant interference. At the end, you have two modes. Okay, they are still split with a 2U in the dispersion real part. So 2U here. But one mode can take all of the losses, and the other one will become lossless. So it's, of course, you need to have the conservation of losses. So the total losses is still gamma 1 plus gamma 2. But then one mode become perfectly interference and take all of the losses, and the one is perfectly destructive interference and become losses. What does it mean if you have losses? That's okay, then the line width become strictly 0. But of course, you need to make this interference configuration happen. So you need to have a good choice of omega 1, gamma 2, U, etc. So I don't need you to remember this. The important features that when you make coupling between omega 1 and omega 2, for example, by changing the wave vector, they cross at the beginning and then you open the band gap to U by the coupling. So the lossless modes will take place from one of the two bands. in the vicinity of the anti-crossing point. So you see here the band gap is open and the mode become losses only at the very specific position in the wave vector space. And now in physics, we call this bound state in the continuum. It's a bound state because there's no losses. It's like a real bound state. In the continuum, because this takes place at the energy that in general you can couple to the continuum. So it's a bound state in the continuum. And all of my presentation now, I will write it very short. It's called BIC, bound state in the continuum. Is become lossless at very specific position in the momentum space. And you engineer it close to the anti-crossing, close where you have the band gap opening. Okay, so if I go back to my previous system, things become much easier because my forward and backward modes are almost identical. So omega and omega 2, which is negative and positive group velocity, they cross at kx equal to 0. They have the same losses, so it's gamma, gamma, and then they couple through the continuum. You can show that it's minus gamma. So if you take this Hamiltonian and you diagonalize, what we will have is that we obtain two bands. It's a complex energy. One band, the energy is completely at k equal to 0. It's a normal incidence. A band, the energy is simply real. It's U, so there's no losses. It's a real frequency. So it's a bound state in the continuum. And the other one is minus U plus 2I gamma. So that means this guy take all of the losses. The losses is double to the uncoupled one. And you have here an anti-crossing point is minus U. So basically, for example, by changing the side of U, you can make the bound state in the continuum, the BIC, changing from the upper band, lower band to the upper band. So you have two band with the band gap 2U. So if U is negative, the BIC is staying here in the lower band. U is positive, the BIC is staying here in the upper band because this is given by the energy is U. Okay. And at U equal to 0, you close the band gap. But if you don't have the losses, when you close the band gap, you obtain the direct dispersion. You remember I have two parabola with the gap before, and I close the band gap in my previous part of the talk. I have the direct points. In the case of non-Hermitian system, instead of having direct points, we will obtain what we call exceptional points. So these exceptional points are very special because we have the degeneracy of complex eigenvalues. So not only the real part are the same, what I show you the real part, it's the two red points, it's the real part, they have the same energy, but also they have the same losses. So they have the perfect balance of the loss exchange. If you think of interference, Frank-Wien interference is some kind of exchange of frequency by U, and exchange of loss by gamma. The exceptional point is the position where you have the perfect balance, that you exchange the frequency, though they have the same frequency, the real part of the same energy, and also they have the same losses, so the imaginary part is also the same. And this is a complex degeneracy, and this exceptional points is a very funny result of a non-Hermitian system, because it's not only in photonics, it's also in every kind of non-Hermitian system. The exceptional points, the exceptional points is a strange effect. Okay, so just cite a few. In quantum mechanics, we learned that if you have a system, the eigenstate of the system should be perpendicular one to the other one, right? But if you take the same eigenstate, the scalar product of the cell is 1. So it's quantum mechanics towards that. But in quantum mechanics is when you have the Hermitian system. You use the quantum mechanics for non-Hermitian system at the exceptional points. The eigenstate is perpendicular to itself. And the two eigenstates, because here we have two modes generated, the two eigenmodes are not orthogonal one to the other one, but orthogonal to itself. This sounds very strange. So a lot of people now doing new things in this non-Hermitian physics based on this exceptional point feature. What is important in this scheme that you keep to remember that we have band gap opening. When you have band gap opening, you can have lossless state bouncing in the continuum BIC on the band edge. And then when you close the band gap, you can emerge exception points, very peculiar features. Okay. Now, let's go to the real world. We try to fabricate and to make the sample happens. Okay, so our samples now is with the low reflective index made of resist, HSQ resist, on top of a Bragg mirror. Okay, so the use of the Bragg mirror is so that we can do some calculation to show that okay the equivalent mode is like when the same thing like when you take out the Bragg mirrors. It's like we have the standing resist grating in air. Okay, so the real structure is with the Bragg mirror. If you perform the fabricate the sample, so it's AFM measurement, so everything works so well. The photonic modes in the system, you remember that we have the band gap opening, so we have the bright mode and the dark mode. The dark mode is corresponding to the BIC. So the bright mode is the one that is symmetric modes in the in-plane mirror. So you go left to right, right to left, you find the same thing. And the dark mode, the BIC modes, is anti-symmetric modes. So left to right, you change the color from violet to green. So you switch sides. So the anti-symmetric modes explain why it cannot couple to the continuum, because plane wave in the continuum is symmetric modes. And so the dark mode is anti-symmetric. So that's why I call it symmetry protected BIC. It cannot couple to the outside because it's anti-symmetric modes. So again, in our experiment, we use always the same. It's a free fraction FF to tune the dispersion. So we follow the dark mode and the bright mode, and I remind you that the gap is 2U. Okay, so by changing free fraction, the bright modes almost stay the same, and the dark modes you can swap it from negative to positive with respect to the bright mode. So we perform the band inversion. At this region, the bright mode is at the higher energy. At this region, the dark mode is at the higher energy. And here we will coalesce the dark and the bright to make exceptional points. So this is experimental measurements versus simulation, and we put on top the simulation, the analytical calculation. So on the left is the experimental measurements. From the right part is the simulation. The dashed line are the theory. So we show what happens when you go from U is negative to U is positive. When U is negative, you see the dark modes is sitting on the bottom band. U is positive, the dark mode is sitting on the top band. This guy is the dark mode is a BIC because at K equal to 0, you don't see anything. I like this concept a lot because when you don't see it, that means it's there. It's like you pick a big people, take a picture of the black hole and show you, this is a black hole. You say, where is the black hole? So you see this is a black hole because you don't see it. So here you know that the BIC, most of the black is there because you don't see it. You see the dispersion is missing a point because light cannot escape outside since it's a bound state. Okay. And then when you make it equal to 0, you see the two, you make this kind of dispersion with the two bands degenerated in the frequency. So we expect that it's exceptional points. So we focus on this. Okay, so it's exceptional point. We follow the resonances, and you can fit the line width, give us the imaginary part, and the position of resonance give us the real part. And you compare it to the simulation, and we see also that indeed at these 2 points you have the degeneracy, simultaneously of the real part and of the imaginary part. Okay, so we have the exceptional points, and like I told you before, that is crazy points. A lot of crazy phenomena take place at this point. For example, the two eigenmodes are not orthogonal one to the other one, and they are orthogonal to themselves. You have also other kind of topological features of the non-Hermitian close to this point. I won't go into detail, except the one that we try to demonstrate here is another crazy feature as exceptional points. That at the exceptional points, the elders is enhanced. For example, you have two modes, left and right. Each one of them has a local density of state. When you make them closer and closer to the other one because make them degenerated, you expect that the total density of state should be equal to the sum of these two. Okay, so 1 plus 1 equal to 2. But for the exceptional points, you make two more degenerated in the complex plane. And these two theory predict that the local density of state of the exceptional points is higher than the sum of the local density of state and non-generated state. So this has been predicted, but no one has been managed to demonstrate it yet. Antiners, so we have the exceptional points, so we can probe the density of state. So again, coming from previous work with Florent idea, we need to implement a low loss emitters layer here. So we choose one of the best high efficiency low loss emitters in the market. It's a perovskite quantum dot. We spin coat the quantum dot here in a very thin layer, and we use it to probe the emission of the quantum dot and then extract the aldose from this. So this is experimental measurements, and this is the theory. Here you can see that in the vicinity of the exceptional points, the emission, and then we extract the aldose, it enhances to what is not degenerated. It's okay. It has because okay, this is 2, and this is 1 plus and equal to 2. So this is bigger than this 2 is normal. But then if you plot it a different energy, you can see that for the red and the green, for the red is when you are very far from the exceptional points feature, this 1, and then at the exceptional point you don't have 2, we have 256. So we already have 1 plus 1 bigger than 2. So we show that okay, we enhance the density of state at the exceptional points. So for the conclusion of this part, I was quick because I spent a little bit time on the applications. I show you also that we can engineer the complex band structure by using Frederick-Nguyen interference. And the subpropylene scale for the crystals is a very nice platform to study non-Hermitian physics to have about state in the continuum exceptional points. So if I have 5 minutes, I just show you some lasing action from this structure. I don't know if Professor Diab let me say something, or you want to stop there.
Of course, you can continue.
Thank you. So in case I already prepared this, okay, it's nice, this complex dispersion. But before, for the real dispersion, I show you we can enhance emission, doing the downshifting, so far so on. So what we can do with the complex dispersion? So in our group, we do a lot of application for lasing. And nowadays, one of the important feature of laser system is to apply for LiDAR. You know, the LiDAR is you have some kind of laser that is scanned, and then by measure of the scattered light, you can reconstruct by artificial intelligence what is in front of the car, and then for the modern car is very important, this LiDAR system. But how to scan the laser beam in angle like this? So if you look at the Google car, for example, when you see the Google car to make the street view, you have some kind of mirror rotating on top of the car. It's based on some kind of rotating mirror. It's a mechanical system. So what we want to do is try to have this light emission at high angle for lasing system, but without having any kind of mirror, because okay, we want to have that our laser emission, instead of having like just vertical emission from in a pixel, we have it like very high angle. This is the idea. So our solution is very simple. You can engineer, for example, in my previous part of the talk, the real part dispersion, we have some kind of valley dispersion like this. You have the local minima, is not a normal incidence. We put the gate material here, and then you can make it lasing. Okay, so you have slow light, high oblique angle, and you have high quality factor. For example, you put the continuum here, you have 0 losses for 3 modes, make it lazy. And of course, all of this is made happen by using the Fine interference. So I need valley dispersion with very high quality factor, so low losses. So I won't go even into detail how we optimize the structure, but it is a perovskite-based material, so it's emitting in the green. We call this MRPBR. So it's you have the organic chain and then the perovskite with bromide perovskite emitting in the green. So it's a 2D photonic crystal, vertically broken as a symmetry, and the lattice is not a square lattice, it's a rectangular lattice. So the period along x-axis is slightly different than the y-axis. And this anisotropy factor eta, this is close to 1, this is very important. Yeah, so because I go very fast, that's in the dispersion of the simulation, you can see at oblique angle, the dispersion vanishes locally. So here is bounded in the continuum. And then this one is from the interference of 3 modes, not 2 modes. So it makes it to bounded in the continuum at kx at 4.2 and ky at 0. So it's locally high density quality factor. And we can change where the BIC takes place. So again, the BIC takes place, the k is equal to 4.2. And we can change this wave factor by changing the anisotropy. So basically, by changing the anisotropy of the system, you can change where the infinite quality factor will be. Okay, so this is a concept. So my PhD students, Raphael Mermet, he performed the fabrication of the perovskite patterning using nano imprint lithography. So we can see this is, we imprint it with a silicon mold. So it's the pattern. Under the pattern mold, is the flat mold, you see that we have nicely the hole in the perovskite. We perform the optical pumping. We see by increasing the pumping, okay, we have the intensity increase non-linearly at some threshold power, and you have the lasing peaks takes place. At the beginning, low power is spontaneous emission. At the threshold, you have the stimulated emission on top of the spontaneous emission, and when you have go to higher power, you only have the lasing emission. And concerning the way it lays, it's important to see why it lays. So it's at low threshold, you see that the photoluminescence populate the whole photonic structure. And here's a BIC. When you increase the pump power at the threshold, you see that the stimulated emission takes place at the BIC. And you still have the spontaneous emission in the background, you know. And at higher threshold, you only see the lasing emission at the BIC, very high oblique angle. Okay, and this is what we predict in the absorption simulation, very close to what we measure below threshold. So this is at Kx, we laser at high oblique angle, and at Ky, remember that the BIC takes place, the Ky equal to 0. So you below threshold, you see the modes. If you increase the power, and at high threshold, above threshold, you see the lasing at Ky non-zero. Okay, so just that we show that we can laser at high oblique angle. I won't show into detail why we have this feature, but basically at the lasing action, if I take out the spectral filter, because now I know that the lasing takes place at the given wavelength, and I image now the whole far field. You have Kx and Ky. You see that the lasing is take place at these two specific angle. One is from Kx positive, that was Kx negative, very high oblique angle. And now let's take back your thinking about the black hole. People show you the black hole image is a ring, right? The black hole is a the singularity inside, and you see only the light ring around. So here the lasing takes place at the BIC, but see the BIC don't emit light. So you only see light escaping from the BIC. So you see that the light escaping from the BIC is in the middle, and light escaping from the BIC, depending on the polarization, because you have here some kind of ring of light. So it's electric field polarization rotating around the BIC. So it's a linear polarization, and then I rotate the polarization, different part of the ring, the donut shaped ring is highlight. So around the the lasing part, I have some kind of a vortex, like you have with water rotating around singularity when you go to your sink. But here the singularity is in the momentum space. So you can show that not only we have some kind of very nice lasing at high oblique angle, but also the lasing polarization show you a vortex rotating. So here, the color here, different color correspond to different orientation of the polarization. So in order to map this color, we perform the measurements of the so-called stock parameters, different polarization, and mapping carefully. You can measure really point by point what is the orientation of the polarization. And this is a calculation from the model and from the simulation. So you see really that, okay, not only you have the lasing at KBIC, but also the polarization rotating around. Okay, so for 1 minute left, I show you this. It can lace on the left and the right. But if you want to go for some kind of LiDAR, I want to have just each go beaming into only one of the corner. So how we can start from the two corner and also now the beaming in the one of the corner. So, I mean, even in the picture suggests you, again, you need to break the symmetry. Now, not the vertical symmetry, but also the in-plane symmetry. So left and right is not the same anymore. Okay, so for doing this, we fabricate another sample now with indium phosphide quantum well, and we introduce some kind of in-plane vertical symmetry breaking on top of the vertical symmetry breaking. So we see that the two elements are not the same. So by breaking the vertical symmetry, we tailor the real part of dispersion to obtain the Vallée dispersion, like I showed you in my first part. And to break the in-plane symmetry, so you see the left and the right is not the same, we tailor the losses and to perform and to obtain asymmetric emission. So this is just how it works. So it is in terms of absorption simulation. You see that absorption in the left and the right is not the same along KX, but for KY is symmetric. We choose the asymmetric. We choose a factor we call the alpha to break the in-plane symmetry so that the asymmetry is high risk. So we optimize emission from one side to the other one. We fabricate the sample. We see lasing. Intensity increase as a function of the power, the line width resharp. And we check if it lays only on one side. This is a case. So this is the measurements below threshold, populate the whole band, but mostly on the right part. You increase the power, it lays only on the right part, so not on the left. Okay, but for the KY dispersion, there is a simulation, here's the measurements, it lays at KY equal to 0 and is emit light symmetrically on the left and the right. So my postdoc student, he managed also to map point by point the dispersion, which comes of tomography, like to show that, okay, indeed we have really this Vallée dispersion and the emission is mostly come from the right. This below threshold, this above threshold. Okay, and you see that it lays only from one side, is it KH and KY. And for this, I finished my presentation because I show you that by engineering the losses and also the real part, you can make, for example, very high oblique angle lasing, but the polarization is rotated, some kind of vortex. Or we can make a lasing, but only in one side of the sample. Thank you for your attention.
Thank you very much, Sơn. I think that, yeah, you show us a lot of things, and even us, we feel tired. So I think that it should be very tired.
Yeah.
Okay, I think it's really very interesting, everything you show today, and we will have a lot of question and discussion, but I think it's time limited. I don't know how long you predict. I mean, you propose for today, Nguyen. We can continue until 11:30, maybe.
Yeah, we can continue until we feel satisfied with the seminar today. So I actually don't have a boundary for that, or limited.
Yeah, but Professor Haisen, he needs to take his 3 children outside today. Okay. Okay, anyone the discussion again for the new part or the old part. Yeah, Nguyen, you can start.
Maybe I can start. I feel really interested in the LiDAR system. So, and actually, I don't understand this clearly. Sorry, maybe may I have a question for the LiDAR system they put in the car? So they need to rotate the laser to scan, right?
Yes.
So, and in this case, you don't need to rotate the laser, and you use a photonic crystal. For
yes,
that
so
right? I don't understand. Could you please
yeah,
sure.
again?
Yeah, thank you.
So the idea is how you can emit light in high angle from a laser, and then changing this angle either dynamically by changing the system dynamically, or you can go to another design close by. Okay. So in the real LiDAR system, they need to have some kind of mechanical parts which rotate very high angle, very high speed, in order to change the beam. I don't have the scheme of the LiDAR here, but you have the laser, you have the mirror, and then the reflection mirror. And then this mirror rotates very fast, so this beam can change angle. This is how they do in the real LiDAR. In our case, what we show is that we can engineer lasing at very high angle. And of course, you can change this angle by, for example, changing the asymmetry of the design. You see, we have two periods. One is AX, one is AY. And you can change the eta, the asymmetry, like few percents, and this angle can change a lot. So one can think of doing this structure on top of some kind of piezoelectric system that you can do some stress to change the size in one direction with this to the other, or simply make few photonic crystals one close to the other one, and making one emit lasing if you want it 20 degrees and the other one is 18 degrees, 16 degrees, because we know how to change this. And it's the same thing for this part. Yeah, so we didn't show dynamical tuning here, but we show that we can have very high oblique angle for lasing, which is one of the conditions for LiDAR.
Mm-hmm.
I don't know if it's more clear.
Yeah, it's more clear, but yeah, maybe I can discuss with you more later.
Yes, sure.
Yes, because
what is the
working
quality
with LiDAR.
Yeah.
What is the quality beam of this laser, Haisen?
You talk about the divergence and that. Yeah. So for example, you see this is in the last one, emit light in the Gaussian beam. You can see is pretty good confined in the. You see, the relativity is very good. This is very localized in momentum space. So it's let's say I remember it's like 2 degrees when you convert into angle is like plus or minus 2 degrees. This beam. So we emit at 20 degrees plus or minus 2 degrees is a divergence, and this one is almost the same, but the pattern is not a Gaussian, it's a donut shape. So you have a donut shape with the polarization rotate around, and also the diameter of the donut shape is about 2 degrees.
That can be good for imaging applications.
Yes. So for example, this kind of we say vector beam lasing, people use this for imaging in biosystem.
Yeah.
Well.
Okay. So Nguyen, to continue to ask the question.
Thank you. Yeah, I'm also very interested in the lasings. My question is why you select perovskite, because as I know that it's not so stable, because when you want to have a lasing, you need to pump the samples with high power. Do you have some kind of degradation?
So actually, first why we choose a perovskite, because because I got the funding on perovskite project, so it's this answer. But of course, perovskite has a lot of nice properties. It's not stable yet, but you can you can have very nice crystal by spin coating, and then we develop in our lab the way how we can direct patterning perovskite by nano imprint. And what happens after nano imprint, that is not only make the pattern as you want here, the whole pattern, but it is also improve the quality of the perovskite. You see, even in the flat part, the perovskite become very flat, monocrystal perovskite stacked to the other one. And the stacking of this grain makes it difficult for water or humidity to go inside the perovskite, and makes our device much more stable. So for give you an information, the lasing still work, even that we don't store our sample in vacuum, and we go for holidays, we go back after 3 months, the lasing still work. Of course, if you expose our system under continuous pumping, then the lasing will die. But if you just perform some measurements and then put it there and then go back 3 months later, it still works. So it's some degree is now, we can say that it's more stable than the organic lasing.
Don't you think to use the for materials like up conversion or down shifting, like they have the emissions very sharp. I mean the full width of half maximum is really sharp comparing to perovskite. Maybe it's easier to have a lasing, with high quality, How do you think about this?
But this material they are not good gain medium, because the scattering cross section is very small. So they are very, so in general, people use it to amplify, for example, the rare earth, amplify fiber. But I don't think you can make a micro laser out of rare earth material. It's difficult, because the perovskite also, what's a good thing of perovskite is very high oscillator strength, so very high line-matter interaction. This emission is visible even with bare eyes. We don't need to have detector. So the rare earth is this oscillator strength is small.
Yeah, I just see that the rare earth materials is very stable, and with the high temperatures, or you can live with ambient conditions for like some years, because I have prepared some for nanoparticles after years, and we use them to give the good emissions. So I'm thinking that if we can use this material to make the lasers,
yes, sure. In terms of stability, yes, rare earth can stay forever. It's like semiconductor quantum well. I mean, the sample will still working even if I die in 30 years. I think in terms of materials, they are better choice than perovskite for sure. It's but again, what we show you here is more in terms of proof of concept, of photonic concept, and we use different kind of materials to show that this concept can be applied for like perovskite, visible lasing, or 3.5 quantum well at 1.5 micrometer on silicon substrate. It's a two different platforms, but then can share the same photonic concept.
I think that the technique of Hyson can be applied for other kind of materials. So I think probably Nguyen and Hyson can discuss to build up.
Yes, sure.
Project.
Yeah.
So I think I will be more happy if people can ask me for collaboration.
Yes.
If we can have in video meetings, and we can share our research more details and
Sure.
Yeah, okay. I will send you an email, and maybe we can set up for a meeting. Yes. Thank you very much.
Thank you, Nguyen. So, Florian.
Thank you. I also have a question on the lasing part. Are you still here?
Yes.
Okay, I didn't see you anymore.
Okay.
Actually,
you don't see me anymore?
It was outside of my screen somehow, but it's actually no. And actually, at this point, I think I should also thank you for kindly accepting to do this presentation in English, and also for the Vietnamese speaker, because it would have been much more difficult for me to understand this part in Vietnamese. So
your name is on the first of the list, you see.
Yeah, thank you. So my question is, I've been mostly working, under the umbrella on emission system, under the umbrella of time reversal symmetry. And this means that we usually always have this symmetry in the dispersion and everything. So it seems that when you are working with non-emission system, you can break this symmetry somehow. My question is it possible to predict how to do this symmetry breaking to decide which side the lasing will occur from the Hamiltonian point of view?
Yeah, so good question. The honest answer is, because you know the story, is that this lasing is something we didn't do it on purpose. So when you are with us, you remember we just want to make it lace in the valley. So
yeah.
and when I perform the measurements, because we didn't think about this in the Hamiltonian, so we think that it should lace in the left and right. And then when I first performed the measurements, it's only lays on one side.
Yes.
And I told my Sebastian Quef, who did the fabrication, I said, you did something wrong. The sample doesn't work. It only lays on one side. And I think that we predict it lays on both sides. And we start writing the manuscript, and we didn't say that it lays only on one side. And one day, it's actually because we did it before the non-emission story start. When we do it says no non-emission part. And then when lately when we start working on a non-emission system, it's actually the system is non-emission. So even that you have the same dispersion, I mean the left and the right looks the same in terms of energy, maybe they don't have the same losses. And then we perform the simulation, and we see, okay, in the simulation, we really have the left and the right don't have the same absorption. So if you don't have the same absorption, then we don't break the time reversal symmetry by the reflexivity feature. We can say that when we emit light, it emits only on the right. And then with this in mind, we go back to the experiment and we check again. And there's also one thing that is unpredicted, because of course you want to optimize the light from the right with respect to light on the left. So by changing the alpha factor, the alpha factor is the asymmetry factor. And by changing this and perform simulation, it's not in Hamiltonian simulation, we see that, okay, at some point the right is much better on the left, and it's when alpha is around 0.1. And we are quite lucky because the sample was fabricated with only one value of alpha, alpha equal to 0.1. So it's why it works well. So everything here is worked unpredicted at the beginning. At the end, we managed to answer, but then we don't have numerical model for the losses here. So it's we don't know why it lays more on the right than on the left. So it's still an open question for the Hamiltonian, but for the simulation, it's worked well. So it's and we are happy that we didn't publish the manuscript in the wrong version yet, because now we know that it lays on the right, and it's become much more interesting that it only lays on the right. That's on what side? Yes.
Okay, thank you. Yes, indeed, a good example of serendipity somehow, and we didn't expect this result, I remember. So
yeah, yes.
Okay.
Thank you.
Thank you. So, Nguyen, please.
Yes. Thank you for the talk. It's a nice talk. So I would like to ask a question, because my work is not related too much with the crystal photonics, but actually it's not a question, because maybe in the future I will send an email for you, because I'm working with hexagon boron nitride material. Yes, so for really familiar with graphene, but actually now I'm concentrating doing with fabrication stuff only. So maybe I saw you have some structure with the pattern, with the valley pattern. Also, we make it like stem. then I will send result slide for my side, and then maybe you have some idea how we can use such a material for the photonic application, maybe, and also you have some direct suggestion for me. So I think that's
sure.
Or not. Yeah.
Sure.
Yeah.
Sure.
Yeah. Okay. So
Thank
then
you.
after the meeting, I will send you a couple of slides for result, and then maybe you'll have some suggestion for me. So thank you so much. Yeah.
Yes. I'd be very happy to have discussion with you.
Yeah. Okay. Thank you so much. Yeah.
Okay. Thank you. Thắng, we discuss again.
Hello. Thank you very much. Also quite interesting. Yeah, in the first talk, first part of the talk, you talk about this. Many focus on Hamilton systems, and now you Hamilton's. Yeah, sorry, my spelling is not so good. And then I was also thinking, you may also discuss this non-Hamilton systems later, and then it came with quite interesting topic, and we were also really interested in this. Can I have a question about this? The emissions, the paper that you saw at the beginning, emissions of
you talk about this lasing or
this, no, the first part. Yeah, this lasing process. From
perovskite.
From the first part.
You talk about this.
Yeah, exactly. So in the structure you use this HHQ as a grating structure, right?
Yes.
Directly. So have you considered the emission from HHQ, because it also absorbed in UV rays around 300 nanometer, 300 something, and it also emitted quite broad from 400, 500 to up to 800 nanometer. And have you considered whether the emission also come from HHQ, or is mainly from the quantum dot, the embedded quantum dot in the system?
So thank you for the question, because indeed HHQ emit light, and that's things that we learned very lately. I mean, before this work we learned lately, because HHQ is known for first like e-beam resist, right? Because you do the lithography, and then it's a resist, and when we do annealing of HHQ, it becomes glass. So it's very nice if you want to make glass pattern. In some works that I don't show here, we work with single photon emitters and quantum emitters that emit very low light, and in silicon. So we use HSQ like the mask, and then we transfer the HSQ pattern into the silicon, and then we perform the measurement, and you see a lot of emission that we don't understand where it's come from, because we expect to have like single quantum emitter, very low light, and then you have this broad emissions, very ugly. And then we understand that it's come from the HSQ, that we need to remove it. So yes, depending on what kind of comparison we do, if I compare to quantum emitters that emit very low light, then the HSQ is very annoying. But then in this work, actually, compared to perovskite, the HSQ is nothing. The perovskite, you shine a piece of laser, you see bare eyes light. So we neglige. So I mean, the emission here is like 99% coming from the perovskite, because the emission oscillator strength of perovskite is very strong, and we have a lot of perovskite quantum dots, not a single quantum dot. So of course, for the single quantum dots properties, it will be important to take into account that the HSQ will change a lot, and maybe we should go to other kind of resist like SU8 or something else that is have low loss. But for ensemble emitters, then like this one, then the HSQ emission we check carefully, because we know this before this work. Now we know this before, that the HSQ can be very annoying, and we check that without the perovskite, with the intensity of the emission is almost nothing compared to with the perovskite. Yes, that is a good point, very good point to raise.
Thank you. And also here you mainly observe EP at the gamma point. Have you see or really look at higher angle, for example, second part, right? You see that the higher angle, but for this structure, have you looked at and see whether you have EP at higher angle or at only gamma point?
Yes, because here the EP is designed at close to the gamma point.
Okay.
Yes, so we there are other schemes to make EP at high angle, but not in this this kind of design, because basically this design we coupling propagating counter-propagating mode. So the gap is at gamma points. For the second part, I couple very high diffractive on the mode, so it's take place at high angle. Yeah.
Thank you. Very interesting. And yeah, you also consider this for LiDAR applications. Yeah, for LiDAR, not only the large angle emission, but also we need to steer the angle. It's very important for automotive vehicles. But for exceptional points, for EP and for non-emitting system, it really depends on how we control the loss and gain. And have you considered whether you can control it, kind of like actively?
For the exceptional points, I mean, there are papers in the literature, they show that they can control this actively by, for example, using liquid crystal. So you put liquid crystal on top here, you introduce some kind of anisotropy that you can, a reflective index that you can dynamically change. So by putting some voltage, they can engineer this. A very nice paper in Nature Communication just coming out. So it's not photonic crystal, it's like peripheral cavity. So you have black mirror, liquid crystal, and then black mirror again. So by changing the liquid crystal, you change the tensor of the reflective index. So you can engineer the coupling between T and TM, the peripheral, and engineer EP. And they can make EP like merging, splitting very nicely. So this is the paper from the Polish group. And in our group, we are trying to do the same thing also, but not with liquid crystal. I have also a colleague in my office colleague. He worked with phase change material. The phase change material is a material that it changes the phase, for example, from amorphous to crystal, or from semiconductor to metal, for example. This is a different phase by changing the temperature or by other kind of excitation. So we want to use it, for example, for this black layer, we can use it like a PCM phase change material, and we can dynamically tuning the dispersion. This one now is an ongoing project.
Interesting. You also mentioned it can be used for example, quantum sensing and things. Could you give us some like insight? How would you apply this system for quantum sensing?
So we don't do the quantum sensing, but people use exceptional point for like high sensitivity sensing, because you can see the dispersion here close to exceptional point. The slope go to infinite. You see it's better here. So and this law can be fit by a square root. So if the square root, instead of having linear, you have some kind of square root. And people said, okay, if we have this square root dispersion, that means sensitivity is nonlinear, come with respect to the perturbation at low perturbation. So for example, you have the, in general, if you have some kind of perturbation, then the detection will be linear respect to the perturbation. So this is how the normal sensing works. But for the exceptional point sensing, if you have a small perturbation, but this perturbation in terms of sensitivity will be increased nonlinearly. So this is how people working with exceptional point sensing. We are not working on this scheme. What we are trying to do also is to make lasing exceptional points. This is again the sensing or trapping is like the know-how of the experimental setup, and in our experimental setup, we are most like detecting light escaping. So it's lasing is a good scheme. Yeah.
Thank you. Yeah, actually, it's in our team together with Florian also working in the same team with me, and also we really focus on the sensing. And I think this could be a very nice approach to use this EP for sensing applications. For example, coupling between the mechanical system with optical system for sound and ultrasound and.
But I heard that there's still a big debate now on the sensing, because they say that you enhance the sensitivity at the exceptional point also enhance the noise at the exceptional points.
Exactly, yeah.
So maybe at the end you don't gain as much. This is a big discussion now. Yeah.
Okay. Thank you. Interesting. So sorry it's taking too long time. Other colleagues. Thanks.
I don't see any other hands, so I try to ask myself some question. Hasan, is possible?
Yeah. Yes. Go ahead, India.
Okay. So can you? I know that for the case of 1D or even 2D, 3D, people they try to fabricate quasi-crystal, and they also produce the flat band gap. So what is the difference between the case of coupling two 1D grating, 1D photonic crystal, and compared to 1D quasi-crystal?
Yes, excellent questions. As what I show you in the moire part, because I think the flat band you mentioned is more like on this moire because we have the real flat band. In the moire part, we engineer the two layers so that we can define a supercell. So we are not in the quasi crystal regime because you can define a real period. And then the flat band is only takes place at some magic configurations. So you, in general, it's not flat. So in general, we don't have localized state. It's delocalized state. But then at some point, at some parameter choices, you have this magic localization. You can say that is. But then if you change it, it's not localized anymore. So it's very different than the quasi-crystal. For the quasi-crystals, you have like a phase diagram. And in some phase, you have the localized states. Because we are trying to do this ourselves, so maybe I can reason a little bit. So for example, I can choose A1 and A2. So that's the ratio between them. It's not the rational number, it's an irrational number. Then the system is not periodic anymore, and you cannot define a periodicity. You need to distinguish as a quasi-periodic system. And the quasi-periodic system is not trivial, the unnecessary localization. So at some point you need to change the parameter system. So have to have unnecessary localization. So you have this flat band like INDF says because you localized it in the quasi-periodic system. And then you can change another parameter and you go to the phase that you have not unnecessary localization. So this phase is not like accidentally you have some kind of really interval of parameters that you have either localized or unlocalized. In our case, it's very at the specific condition. So it's in general, it's not localized, and you need to have this magic configuration to make it localized. But our future works also in a theoretical work, we try to also do this quasi-crystal system to see if we can reproduce this mobility edge. Means that the phase transition between unnecessary localization and non-localization for the quasi-crystals.
Yeah, thank you very much for the explanation. Technical question in the case of exceptional point, what is the role of Bragg mirror? Can you go back to that? I think because I am our project, but I don't see clearly the role of Bragg mirror.
Yeah. Okay, so the Bragg mirror is a trick because I want to close the gap, right? Because the exceptional point sequence close the gap. If I want to close the gap, then I need to have low refractive index contrast.
Yes.
So you see, most of my work before was with silicon. Silicon is high refractive contrast. So the gap is open like crazy. So the silicon is good to make flat band, to make like interacting spaghetti. But if I want just band slightly interact, I shouldn't use silicon. That's why I should have like low refractive index. Now, what we should use like a low refractive index, I can either use a glass substrate and making silicon nitride grating on top. But then I still need to have etching and doing a lot of fabrication techniques. So we figure out this nice scheme. We say, just make a grating of resist, because resist is the refractive index. But then if I have the resist on top of glass, it doesn't work because the glass, the substrate is the same refractive index as the resist, okay? So if I have a grating of resist, I need to have the resist standing in air. But I cannot fabricate it, so it's complicated. So the Bragg mirror mimic the air on top. We can simulate, you can see that the band structure if you have the black mirror or if you remove the black mirror, it's the same. So the black mirror is some kind of like imaging. You remember when we doing like charge image in electrostatic. You can put the mirror and then you have one charge, you have the image charge on the other side. You can think of this black mirror make an image, so you have this grating and the second grating below. So it's but you double the thickness. So it's so the black mirror is a trick to make low reflective index for the crystal without any etching. Yes. But we can discuss later on our project.
Yeah, sure. I also have some idea to replace black mirror by other what we did here, so it's good point.
Yeah.
And another technical question for all the simulation and also fabrication by E-beam, the 1D photonic crystal have a square or rectangular shape. So if we replace that by sinusoidal shape, what is the result? What you predict?
You talk about which shape?
The shape of the 1D photonic crystal.
Yes.
You see the design, what you show here is like a rectangular or square shape, right? But in practice, we can fabricate the structure with the sinusoidal shape.
If you can do it like vertical symmetry, this will be very nice. If you have like instead of having vertical edge like this, you have to make it like this. You see, people, then you can do very nice engineering. People try a lot to do these kind of things. Of course, also we can break also the symmetry by instead of having this shape, making some modulation. Is also we didn't do this because we don't know how to fabricate it easily. But yes, more degree of freedom. We put more flavors into this system for sure.
Okay, so I think we can discuss about that for our project.
Yes.
So we have flexible technique to fabricate, right? So we can do.
Yes.
Okay, I don't want to take time of all other people to discuss about our project, so I will stop my question here. If other have a question or discussion, we can forfeit the time with Professor Hải. Cương, please.
Không, em chỉ vỗ tay thôi. Yeah.
Okay, if no other question, probably we can stop here. So we thank Professor Hải for the excellent talk and all the sharing results today with us. Thank all participants, and I think that Hải, you got a lot of collaboration now.
Yeah, so I thank you again for Cương for inviting me to this nice network and also this opportunity to give my presentation, and also I give a very nice chairman that knows me perfectly well, and especially I want to give a mention for all of my collaborations. So everything I show you here is not my work of me alone. It's actually a fruit of a lot of collaboration within my group at INL. So you see that's PhD student, postdoc, and permanent researchers working in both fabrication, simulation, and measurements, and also my collaboration from outside. So the first line is all of the collaboration in terms of the theory, and then people giving me materials for and also some collaboration for the measurements. Yes, that's and just last work that also my thanks for my fundings, and just mentioned that we have also a poster position opening on the theory of non-Hermitian topological photonics. So if you know some good candidates, it's will be very welcome. And this position is a collaboration between me and my friend Nguyen, who now has a permanent position in Korea. And so the work is basically between France and Korea. Yes.
Starting from when?
Whenever you want. I mean.
Can recommend you some good candidates?
Yeah.
And maybe you can send the information to me so I can upload to the website, so maybe more candidates will.
Yes. Sure.
Okay, so thank Hải and thank everyone. Thank Cương, thank everyone.
Yes.
So let's Cương to say something.
Yeah, no, yeah, thank you very much, Anhaisen and Andrew, for giving a talk and also sharing the seminar. It's very interesting, and I hope that we will have a more collaboration after this seminar.
Yeah. Sure. Yes. So thank you, everyone. And
I just stop recording now, and maybe if we want to discuss some more, we can continue a little bit.
Yeah.